progress on, or quite a bit of progress on, developing an algorithm for computing eigenvalues. As we're talking, everybody's looking at their laptops. Not annoying at all. Okay. So today's kind of arrive at a practical algorithm of a general matrix. So to remind you of so my apologies for interrupting whatever you're doing. Now, where we're at to this point. So just the algorithm, in a nutshell, is we use householder, and I don't feel like writing out householder reflections, so I'm going to call them householders. We all know what that means. So matrices that carry out householder reflections. Compute householders, P1, P2 up to Pn minus 2, so that A times all of those householders multiplied on the right, and then in the opposite order on the left, equals matrix H that is Hessenberg. So all entries below the first subdiagonal are 0. And then, once we do that, we repeat so long as we are not convergent, we take that matrix H and we compute its QR factorization, and this will take order n squared operations because of the Hessenberg structure, and it makes sense in this case, even though we have 3 approaches for QR, the only one that makes sense in this case is Givens rotations to 0 selectively those n-1 subdiagonal entries, and then multiply with factors in reverse order, also using Givens. So it's just a Givens row rotations to reduce H to upper triangular form. So really it's Q transpose H is equal to R, where Q is G1, G2, up to Gn minus 1. So n minus 1 Givens rotations to eliminate those n minus 1 subdiagonal entries. And then here we take that matrix R that we got from the previous step and apply those same Givens rotations on the right, because that is Q. So we never explicitly form Q. We don't have to, unless we really want the eigenvectors later. And that's where we're at as of last time. So we have an algorithm that is only order n squared work per iteration. So that's good. But it will converge too slowly. If you happen to try that MATLAB snippet where you take A equals QR and A equals RQ, they keep overriding like that. So it would take a while, eventually converging to some sort of upper triangular form. But we need to speed that up, and that is what today is about. So to get an idea of how we can do that, the main idea, what we'll do is use shifts. So the idea is, given, because we want to get all the subdiagonal entries, The whole point of this QRRQ process is to make all of those subdiagonal entries eventually become 0, or so small we can just declare them 0. Now, how rapidly do these subdiagonal entries go to 0? Well, we have some information about that. So the p subdiagonal entry of h goes to 0 at this rate, lambda p over lambda p plus 1 over lambda p, where lambda 1 is the largest eigenvalue, then lambda 2, and so forth. So the eigenvalues are ordered by their magnitude. So this ratio is guaranteed to at least be less than or equal to 1, but if it's close to 1, so if the eigenvalues are really clustered, then that's a big problem, because then that's what causes the slow convergence. So what if we shift instead? And by that what I mean is, instead of QR factorizing just H, our Hessenberg matrix H, we shift all the diagonal entries by some value mu. So mu is a scalar. And we subtract mu from all the diagonal entries, since we're multiplying by identity, which has ones only in the diagonal and nowhere else. And we QR factorize that. Then, the new updated H, we go ahead and carry out RQ, and then we add the shift back. So what this means is, to show you why this is, first of all, even correct, this would mean that R is equal to Q transpose times H minus mu I. So if I dump that in there, so R is Q transpose H minus mu I Q plus mu I. And what will happen is, then I'll get Q transpose HQ, which is what we had before, and then minus mu Q transpose Q plus mu I. But Q is what type of matrix? Orthogonal, and therefore Q transpose Q is identity. So minus mu identity plus mu identity. So these terms all cancel out. So the new H is equal to Q transpose old H times Q. And what do we call this kind of expression? Similarity transformation, which does what? Yeah, so pop quizzing you every time works. Okay, good. Let's get a little numerical linear algebra robots. All right. So it's still a similarity transformation. It's just that this Q is not going to be the same as the Q when there's no shift. Because by subtracting mu from each diagonal entry, you're changing all the columns. So when you're making each column orthogonal of Q orthogonal to previous columns, you're working with a totally different vector space. So what happens, what's the convergence rate in this case? It's the same as this, except because of a shift, we subtract mu. in both the numerator and the denominator. So this quantity is going to be much smaller if mu is close to an eigenvalue, like mu is close to lambda p plus 1, because that would make the numerator nearly 0 over something non-zero, hopefully. So that now boils down to, if we choose to shift right, we can achieve rapid convergence. So how do we go about choosing a shift? All right. Now, this fraction here shows us we want mu approximately equal to some eigenvalue. So we know that will help us. Now, to give you an idea of just how much it can help to achieve that, I'm going to discuss a problem that it's actually one of the explorations in here. So I might assign it to you, so therefore I'm not going to prove it. The result is important to know anyway. And actually, it's not a terribly hard problem. It's an annoying problem because you'd be writing out matrices of all those x's like I did. See how much fun it is. So, if mu is an eigenvalue, so suppose you get lucky and you choose a shift that has to be equal to an exact eigenvalue of A, then a new h, as if I write out the structure of the old h versus the new h. So the old h is some upper Hessenberg matrix. Okay, with this. What?
So I'm going to set you up.
Okay. So there's this diagonal with all non-zero entries. What will happen is the new h that's overwritten with Q transpose HQ will have this structure. That's almost the same. We get a 0 in the last position of the subdiagonal. And that is huge because the matrix is now block upper triangular. So the eigenvalue problem is now decoupled. So we have, in other words, that is an eigenvalue. This last diagonal entry here, in fact, it's equal to mu. So actually, I'll write it this way. So I'll fill in mu there. But just because of the structure, it's an eigenvalue. And then you can focus on this unreduced Hessenberg block that is smaller. So you just reduced the size of a problem. So your next QR iteration will be only on that block. You can forget about the last column and last row. So then your whole process is going to speed up because I just said that each QR step, so h equals QR, h equals RQ, with a shift, takes order n squared operations. But now n itself is getting smaller. So that's going to cause acceleration of this whole process. All right. So, and in words is if we, this is actually taken from Gall and Van Loon, if we shift by an exact eigenvalue, deflation, in other words, this decoupling effect here, where you separate one eigenvalue from the rest. Deflation occurs in one step. So we don't normally expect this to actually happen. I mean, well, how likely are you to choose a shift to be exactly equal to an eigenvalue? But if we choose it close to an eigenvalue, this gives us hope that we can cause that last subdiagonal entry to go to 0 rapidly, and at least get fast convergence. All right. So this leads to what's called the single shift strategy. You choose mu equal to the very last entry in the matrix, the NN element. So that's in the lower right corner. So the idea is if your shift is approximately equal to some eigenvalue of A, then this matrix, H minus the shift, is nearly singular. So if that matrix is nearly singular, that means that the NN entry of R is going to be nearly 0. Okay. And because of that, in the new H, row n, column n minus 1, that's going to be nearly 0. And I don't want to go into detail why, because that relates to that homework problem that I might assign. But it goes to what I was showing you last time, where you're applying these Givens rotations. Each one is rotating only 2 columns. So when you're applying all those Givens column rotations, this entry comes about from rotating the last 2 columns. So if this entry is nearly 0, and it's sitting next to an entry that's exactly 0, you perform this Givens rotation of columns, it's going to cause this entry to be nearly 0 also. So you have an approximate decoupling. So what I'm going to do is show you, theoretically, why this shift can be effective. All right, so I'm going to use a subscript here. So I'm trying to talk about H and new H. So I use HK and HK plus 1. So K is the iteration counter. Okay. So okay, actually, yeah, the algorithm in my book, I had written out using indices. So for the sake of your notes, I'm going to rewrite this using indices, so you can clearly distinguish new from old. And the shifts are going to vary from iteration to iteration. So it's going to label them mu1, mu2, mu3, etc. Okay, sorry about that. Now, so let's suppose I'm going to show what's going on with just a 2 by 2 example. So we have some entries up here, and then we have some entry epsilon. That's the subdiagonal entry you want to get rid of. And then, let's see, actually, okay. I'm going to set this last entry to be 0. In other words, this is a matrix we're dealing with after we shift. Because that's what happens in a single shift strategy. When you subtract the last nn entry from all diagonal entries, that very last diagonal entry is going to be 0. So in the book I have it worked out, like if you try to reduce this to upper triangular form. So this is a 2 by 2 matrix, so you only have to zero out this entry. So so my new matrix HK plus 1 is going to be QK transpose HK QK. And QK in this case is just going to be a single Gibbons rotation, because that's all we need. So QK is going to equal C minus S SC, where that's the Gibbons rotation needed to zero out this entry. And so C is going to be A over square root of A squared plus epsilon squared, and S is going to be epsilon over square root of A squared plus epsilon squared. So when I derive Gibbons rotations, when talking about QR factorization, these would be original formulas for C and S that have to be adjusted because of floating point arithmetic, but we're not worried about that here. So this one Gibbons rotation is enough to zero out this entry and compute QR factorization. And then we multiply by that on the right. So if you carry out all the multiplication here, all the matrix multiplication, what do you get? So I'll just cut to the chase here. But it's all worked out in the book. So we have A plus BCS. And then I have BC squared minus epsilon. And then I have minus BCS here. And then I have minus BS squared. Although that's not really illuminating until we fill in what C and S are. These entries right here. We really care about the subdiagonal entry. So if I fill in S squared, so that's minus B epsilon squared over epsilon squared plus A squared. So what just happened here? It's actually kind of a big deal. So the old entry in row n, column n minus 1 is order epsilon. So in this case, it was exactly epsilon. Then the new entry, I forgot to actually say that. The new entry, row n, column n minus 1, is order epsilon squared. In other words, it goes to 0 quadratically. Those of you who, well, yeah, a little more than half of you, who were in my numerical class last spring, we saw an example of quadratic convergence. What was it? What? No, fixed point was linearly convergent. Yes. Newton's method for finding roots was quadratically convergent, and what that meant in that case was whatever the error was after a certain number of iterations, the error after the next iteration was proportional to the previous error squared. So when the error is already pretty small, what does squaring do? It makes it a whole lot smaller. So why is this so important? Let's suppose that epsilon is, say, 0.1, so 10 to the minus 1. Then you carry out these iterations. You get 10 to the minus 2, 10 to the minus 4, 10 to the minus 8, 10 to the minus 16. 10 to the minus 16, that's like on the level of just round-off error. So negligibly small. You can pretty much declare it 0. So that means that it basically imposes a bound on a number of iterations you can possibly need. It's a rough bound, because you have to get this thing to be small in the first place. But the point is, it's going to go to 0 very rapidly. So this is an effective technique towards achieving rapid convergence, that we only have to expend a handful of iterations, 4 or 5, something like that, per eigenvalue to get all of them. So and this would be a big improvement over a number of iterations if we weren't doing any shifts. So this is so now we've made a big step forward towards getting a practical algorithm for computing all the eigenvalues, just by using this single shift. In fact, what I can say is, if it is known, for whatever reason, and some applications it might be, that the matrix A has only real eigenvalues, then we're done. We could just do this. We could just use it's a Q iteration. We could just reduce it to Hessenberg form first, then just carry this out. And every 4 or 5 iterations or so, a subdiagonal entry will be driven to 0. Now, how fast it really happens depends on a number of things. Like, if certain eigenvalues are closely clustered, that will make it take longer. But generally, every few iterations, you're going to make some subdiagonal entry 0 and see, oh, there's an eigenvalue. The problem's getting smaller. And you can keep working on these unreduced blocks. So again, each iteration is getting faster than the one before, simply because you're dealing with a smaller matrix. Now, one class of matrices that is known to have real eigenvalues is symmetric, which I'm actually going to talk about on Monday. In that case, because of the symmetry, an even faster convergence is possible. Instead of using the NN entry as a shift, so you could do that, certainly from a symmetric case, and it'll work. But there's another shift called the Wilkinson Shift, which I'll get into then, that makes convergence cubic, so even fewer iterations necessary per eigenvalue. So if we know we have real eigenvalues, it's Miller time at this point. We have a practical algorithm, but we're dealing with a general n by n matrix. We can't assume that it has real eigenvalues, so we have to be able to handle the complex case. But first, any questions about what happened here in a real case? Yeah.
Before we did the givens, I don't really know the pattern, the notice following. First, you said HK is that. The shift.
Okay, what part of the board am I looking at?
The first one.
Okay.
Left side or the right side?
Let HK go.
This?
No, the very first time.
Yeah.
Yeah. Is that the new or the old?
This is the old.
The old one. Okay.
Yeah, so in other words, so this is a matrix we currently have, but then we carry out the shift. And the thing is, the shift is by the 2-2 entry. So we subtract the 2-2 entry off, we're going to get 0 here. So this experiment here is kind of simulating that. So here I've written out the algorithm for whatever shift you're using, but from a specific case of shifting by the NN entry, the matrix you're actually QR factorizing is this one. And that determines the Q, because you're QR factorizing the shifted matrix. Other questions? So what about complex? All right. Well, I have almost an hour left of class. It'll probably take that long to explain it. I can honestly say what I'm about to show you is probably the main reason why I love numerical linear algebra, even though I'm really more of a numerical PDEs person. But just, I have to admire the genius involved in the people who came up with this. And it's just funny that the guy who came up with it did not know he was famous for like 40-something years. But it's funny how these things work. But at least he got to find out in the end. Okay, so what about the case of complex eigenvalues? So in that case, shifting by and taking the NN entry, it doesn't really help. We still have the same kind of slow convergence that we would have when we weren't doing any shifting at all. So what can we do? We can use a pair of shifts. So this workaround is called the double shift strategy. So we use a pair of shifts, mu1, mu2, which are equal to the eigenvalues of, so instead of working with just the NN entry, the lower right corner, we take the lower right 2x2 block. Because it's very easy to get to the eigenvalues of a 2x2 matrix exactly. We're just using quadratic formula. Now, if these eigenvalues happen to be real, it's kind of like using a single shift strategy twice. And in fact, it would maybe even help. But if they're complex, then these eigenvalues would be complex conjugates of one another. So, in other words, I'm suggesting using complex shifts. So what happens in that case, for each iteration, is the following. So you take H, and we subtract off the first one of these as a shift. Go ahead and compute a QR factorization. And then H1 will be the updated H with the first shift. And then we just carry out again. With the second shift, H1 minus mu2 identity is Q2R2. And then our updated H is H2, where you carry out the same process with Q2, R2, and mu2. All right, so we're just doing all our iterations in pairs now, but it's still the same kind of iteration. All right. Okay. Oh, let's see, we're still writing going on. Okay.
Apparently, I need to cover half as much in each class, and you guys can write it all down. Okay. 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 Now, the problem is, so now when you've written down this approach, I can tell you why it's awful. H we're assuming is real. But all of this, these are complex numbers. This, H2, should be real, even with these complex shifts, just because you have the shifts being conjugates of one another. And I say should be real. In practice, it's not going to be, just because of round-off error. These, like Q1, R1, Q2, R2, H1, all of those are definitely going to be complex. Now, I don't know if I brought this up before, I probably did, but just to refresh, we really want to avoid complex arithmetic if at all possible. Because adding and subtracting complex numbers takes twice as much space and twice as much computation, because we're going to work on the real and imaginary parts separately. Multiplying two complex numbers, aside from the whole twice the space thing, you also need at least 3 floating point operations on real numbers. So, so we're really making us take a whole lot more time. So if there's any way we can avoid that, to cut down the expense of the algorithm by half or maybe 3 times, we really want to do that. Okay. So, okay. So, how we can get around that is a lot of manipulations to work with matrices that are real from start to finish. The fact that these two shifts, mu1 and mu2, are complex conjugates is going to help us. Now, before I continue, I do want to point out the one dilemma that led us to do this in the first place, the fact that we have slow convergence. We have solved that problem, by doing complex shifts. So we don't have to worry about that anymore. So at least the QR algorithm using either, like what we could do is go ahead and compute the eigenvalues of this matrix. If they're real, we could use either a single shift strategy over 2 real shifts we get from this, or we can get, or if they're complex, we're using 2 complex shifts. Then we get reasonably fast convergence of the QR algorithm to get all the eigenvalues. So that is an important achievement. It's just that now we want to try to do this without any complex arithmetic, because yes, we speeded things up by using these shifts, but now we've given back some of the speed gains by doing complex arithmetic. We want to claw back those lost gains. Okay, so what can we do? So I have this written out here in the book, but I'm not sure if it's the best order to use. Oh, okay. So I can define this matrix M to be h squared minus, well, actually, you can write it out this way. H, what?
It's just we write and then you erase it and then you're waiting for us to finish writing.
Then do a tape delay like a TV networks.
It's funny. We're just laughing.
Okay. I thought I heard frustration or something.
No, we just put our pens down and all giggles.
Yeah. Okay. But I mean, you especially, you've been in my class for 5 years. You know.
Yes, I know.
Yeah. Okay. So this
That's
would be.
why I was the last one writing.
Oh, okay.
I waited.
It still wasn't enough. Okay. plus mu1, mu2 identity. Now, even though mu1 and mu2 are complex, because they're complex conjugates, these numbers are real. This is equal to 2 times the real part of mu1, which is the same as that of mu2. And this is equal to the complex modulus of mu1 squared, the magnitude of a complex number, which is a real number. So really it's real part squared plus imaginary part squared. So M, even though it's formed from complex matrices, is a real matrix. Also,
Is that RE, and is E a subscript?
oh, that's one word, the abbreviation for real part.
Okay.
Well, I understand you've never taken a complex analysis class, so yeah. Okay. Okay. Now, if I were to, okay, I work with this factorization here. So H is, so here I have H squared. So H from over there is equal to Q1 R1 plus U1 identity all squared. Okay. Minus U1 plus mu2 H, which again is Q1 R1 plus mu1 identity, minus plus U1 mu2 identity. Okay, so if I were to multiply this out, the word might not work quite how I wanted. Let's see, Q1 R1, Q1 R1 plus, I'm just foiling here, 2 U1 Q1 R1 plus U1 squared, okay, identity, minus U1 plus mu2 Q1 R1 minus mu1 plus mu2 identity plus mu1 mu2 identity. Now, fortunately, I could do a little bit of simplification here, because here I have minus mu1 mu2, and here I have plus mu1 mu2. So that term is gone, and that term is gone. Now, I want to be able to work Q2 and R2 into this, and here's how I can. Notice here I have R1 Q1, so multiplied in the opposite order. And I have that over here. R1 Q1, but I still have Q1, and R1 Q1 is equal to H1 minus mu1 identity. I still have the R1, and then I still have these other terms. And someone tells me I'm going to regret taking all this time doing this manipulation, but right now we're still good on time. Minus mu1 squared identity. Oh, okay, this is nice. We have a quick cancellation.
Ooh, U squareds.
Yes, gone. I also have minus mu1 Q1 R1. and then I have minus mu1 q1 r1 again, plus 2 mu1 q1 r1. So 3 terms are going to go away.
I'm guessing the identity portion doesn't actually matter.
Well, since it's a matrix.
Okay.
Yeah. Okay. And then that goes away,
And then the other minus one.
and that goes away. We still have the mu2, but we'll deal with that in a moment. So now I have h1. But h1, I can use this for, well, anyone watch this later. I can express it in terms of q2 r2. Thanks for no one saying d2.
R2D2?
Yeah.
We've already had that conversation.
Yeah. Okay. So h1 is q2 r2 plus mu2 identity, and then I have still the r1. Okay. Okay. Nothing. Okay. Then I have minus mu2 q1 r1, and that is going to cancel with this. So that's gone and that's gone. So the only thing left is q1 q2 r2 r1. Okay. Now, why is this really significant? Because M is a real matrix, and this is a QR factorization of M. Remember, QR factorization is unique. So if I come up with it any way whatsoever, that is a QR factorization. So the QR factorization of a real matrix is going to be real. Now, here I've used the fact that if you multiply 2 orthogonal matrices, the product's orthogonal. If you multiply upper triangular matrices, the product's upper triangular. So those structures, orthogonality and upper triangularity, survive multiplication. So even though Q1 and Q2 individually are complex, and R1 and R2 individually are also complex, their products are real. So what that means is we can obtain at least these products without performing complex arithmetic. We can form M and then take a QR factorization, and then we have Q1, Q2, and R1, R2. We can't identify the individual factors that are complex, but at least we have those products. Now, that by itself is not yet helpful to us. We need one thing more. Because now we're going to take a closer look at our output, H2. Because after we apply both shifts, we QR factorize and get H1. We do it again, we get H2. So let's take a closer look at H2. Now, H2, what I wrote out before, just erased, was R2 Q2 plus mu2 identity. But now, if I write out, well, okay, actually the easiest way to do this is use the fact that Q2 is an orthogonal matrix. Well, I have to be careful about this. Since it's complex, it's a unitary matrix. Q to HQ2 is identity. Okay. Then what I have is okay. Oh, here too, I'll fill in Q2 HQ2 because it's identity. Now I can factor out a Q2H on the left and a Q2 on the right. So what that leaves me is Q2 R2 plus mu2 identity Q2. Okay. But this we actually saw. Yeah, it's over here. Did I mess something up?
No.
Oh,
Don't
no, I did. No, because I canceled this. I replaced. Yeah, H1 is this.
Yes.
So that's exactly what this is. H1. Yes, thank you for forcefully asserting I've not messed anything up. Okay. Well, I can do a similar cycle of operations on H1, and where instead of R2 and Q2, I have R1 and Q1. So, and the rest of the stuff's written on the book, but it'd be very repetitive. I get Q1, H, the original H, Q1, Q2, and using properties of matrix multiplication, I can write it this way: Q1, Q2, transpose the whole thing, H, Q1, Q2. So, H2 is a similarity transformation of H. And in fact, because we know that Q1, Q2 is real, I can go back to writing transpose again. Okay. So, where's this going? What I'm talking about is each individual shift. So shifting by mu1, QR factorizing, shifting by mu2, QR factorizing. Each one of those was a similarity transformation individually. First one involving Q1, second one involving Q2. But there's no reason why we can't do both of them at once, to do it all in one shot. Because we don't need Q1 or Q2 individually, and this proves it now. Our goal is to get from H to H2 in any way we can that avoids complex arithmetic. I now know that this matrix is real. So if I have this matrix, I can do this similar transformation and get H2. And I can do it efficiently. So I know this matrix is real. And I know how to get Q1, Q2 using real arithmetic. So I've already mentioned we solved the slow convergence problem. So now I can describe a modified approach that avoids a complex arithmetic problem. So this is called the implicit double shift strategy. So in other words, we're taking a double shift strategy we wrote about before, and now we're going to fake all of it. It's something that numerical linear algebraists are very good at, faking certain operations. So I'm going to let S be equal to mu1 plus mu2, and T equal to mu1 times mu2. And S and T, as I mentioned earlier, are both real. So we're getting our shifts. We're using a quadratic formula, but we can do that with just real arithmetic to isolate the real and imaginary parts. Our quadratic formula really gives us the sum and product of the two roots. So no complex arithmetic needed to get to this point. It's just quadratic formula know-how. So what do we do with that? I create this matrix M I mentioned earlier. It's H squared minus SH plus T identity.
Is that a 1?
Where?
Is that a 1 with a parentheses behind it? Right next to your capital M?
Yeah. Yes. I'm making a numbered list.
Sorry.
Okay.
That's what I thought.
Well, yeah, the things I write in this board, you never know anymore. Okay. Next, we take the QR factorization of M. So what will happen is Q happens to be equal to Q1 Q times Q2. That's a real matrix. We just never need Q1 and Q2 explicitly. Now, and then, I'll talk more about the structure of M later, but this is best done using Givens rotations, because then you can use that to implicitly represent Q. So you can apply Givens rotations implicitly, efficiently. For a third step, we let H2 equal Q transpose HQ. Again, using Givens rotations. So this step will take order n squared operations. Because you use Givens rotations, you only have a few entries to zero out to represent Q as Givens rotations. Then you're applying those same Givens rotations to H on the left and the right. But H is a Hessenberg matrix. So this again will take order n squared operations because you only have order n rotations. Each one takes order n time, or arithmetic operations, so order n squared work overall. Because that's what we want. We had order n squared work before by going Hessenberg. We had to preserve that. So it seems like we're done. We're not because of that. That wrecks everything. The very first step of forming M, because you're squaring a Hessenberg matrix. That's going to take order n cubed operations. So, whoops. So we solved our convergence problem, we solved our complex arithmetic problem, and now we have a speed problem again. So we're kind of going around in circles here. So, enter John Francis to save the day. If I could find the right page where it talks about how he did it. Okay. That's not what I want. Okay. So hopefully I can explain this just right. This is a real stroke of genius here. So first, the first column of M turns out has only 3 non-zero entries. And the reason why is we're taking a second degree polynomial of the Hessenberg matrix. So a Hessenberg matrix would only have 2 non-zero entries in its first column. When you square that, it's going to add a third one, but that's it. So at least this column has very little going on in it. Okay. So now, that's our first step. We go ahead and compute, instead of all of M, we compute only the first column. Second thing we do is use a householder matrix I'll call P naught, so this matrix, so P naught applied to ME1 is some multiple of E1. So in other words, we're wiping out all the entries except for the first one. Just like in QR factorization, which is actually the point of all this. So a key point here, P naught is the first householder matrix that we would use in the QR factorization of M. And that's important because that's what the second step in our doomed procedure called for, to QR factorize M. So again, we're starting the process. We're just not going to do the whole thing. So we computed the first column of M. We figured out how to reduce it towards upper triangular form, just the first column. But so far, that's all we've done. Okay. Then what we do is we take that P naught and apply it to H. P naught transpose H P naught. Okay. Now, H is Hessenberg, but the result of this is not Hessenberg anymore. We've wrecked that. But that's okay.
Are you sure?
Yes, this is Hollywood regular algebra. It has to be a happy ending.
And there's
Okay. So the next thing we do is more householders. P1.
just bring back Hessenberg.
Yes, that's exactly what happens. Spoiler!
Spoiler alert!
Although it's not the main thing to spoil. So, yeah. So P1, P2 up to Pn minus 2 to restore Hessenbergness, I guess. So now we have H. We already applied P naught on the left and right. And then we'll do the same thing with P1, P2, etc. All the way to n minus 2 because that's how many columns you have to address for Hessenberg form. So in fact, well, no, I can't say that yet. So the thing is, what we've done is we've started with H, which is Hessenberg, applied a bunch of transformations to it. In fact, it is a similarity transformation, and we got a Hessenberg matrix out of it. This procedure also started with H, that is Hessenberg, does some similarity transformations, gets another Hessenberg matrix out of it, H2. H2 is the one we want. But how do we know, why should we believe that the Hessenberg matrix we got here is the same as the Hessenberg matrix that we got here? We don't know that yet.
P2 also transposes.
Is that transposed?
Yes. Yeah. Everything on the left is transposed. Okay. So we have a Hessenberg matrix, but we need to be sure which Hessenberg matrix it is. Now, well, what's happening here? Okay, still good on time. The key here is that everything except P naught, so P1, P2, up to Pn minus 2, they do not affect the first row or column of whatever matrix they're being applied to. So in other words, first row when applied on the left, or first column when applied on the right. Now, I'm going to let, first thing to recall, M has this QR factorization, this plain old, I just named it QR. I call it Z in the book though. Where Q is this product of Q1 and Q2. And I'm going to let Q tilde be equal to the product of all the householders. So P naught and then P1, P2 up to P and minus 2. Now, what we had before was that H2 is equal to Q transpose HQ. I wrote that down before, but that was our flawed procedure that was too slow. If I'm going to define H2 tilde to be Q tilde transpose HQ tilde. Both H2 and H2 tilde are Hessenberg. So here's the kicker at last. Because P1 up to Pn minus 2, so everything at the first, does not affect the first column, Q and Q tilde, they have the same first column. This P naught, like I said earlier, is designed to be the first householder transformation that carries out the QR factorization of M. So if you factored Q and Q tilde as a product of householders that reduced M to upper triangular form, the first household transformations in each would be the same, this P naught. After that, we don't know. But because that's the only one that affects the first row and column, that's why we don't know if these matrices are equal, but we do know they have the same first column. So, because we have two transformations that reduce H to Hessenberg form that have the same first column, what do we know from last time? So this is a situation I talked about on Monday. If you have two ways of reducing a matrix to Hessenberg form, but they happen to have the same first column,
Are you asking what the method is?
well, there's, I'd be careful not to give it away, but what do we know in that case, in that situation? What about the transformations involved? What? I'm sorry, I can't.
It takes the iterations element by element.
Yeah, what about element by element? Right?
That's what he remembers.
Okay.
Remember the word pieces.
Yeah.
And that's all we got.
Nobody?
Say it one more time.
If you have two transformations to reduce the same matrix to Hessenberg form, I called it A last time, but H this time.
Right.
And those two transformations happen to have the same first column. What do we know about the transformations in general? Or the Hessenberg matrix they produce? No.
Are the matrices the same?
Yes. The implicit Q theorem. Oh, you were going to say it?
That's what she said from the very beginning. Sorry.
Okay.
That's why I
Okay. All right. By the implicit Q theorem, H and H2 are essentially equal. So they're equal up to a sign. And Q and Q tilde, their columns are plus or minus each other. So this is how we're able to fake it. Because now, by following this procedure that I've written on this board, we're no longer doing anything that's order n cubed work. I mean, computing the first column m, that's practically nothing. It's computing 3 numbers. Now, household reflections in general they are expensive, like order n squared operations each. But the fact that H is a Hessenberg matrix to begin with, and yes, this does wreck Hessenberg form, but not by much. So you have to be careful how you implement the household reflections. But when you do, each one of these can be made to take only order n work. So now we finally have an efficient procedure, and the result of this is called a Francis QR step. Okay. So everything I've described here. So it exploits the implicit Q theorem to accomplish the same work that I wrote over here earlier that would have taken too long if done in a straightforward way, still accomplishes the same result. And it's the implicit Q theorem that guarantees that it really is the same result. I mean, yes, the signs may be different, but we don't really care about that because we're just trying to make these subdiagonal entries 0, which is going to happen either way. So that leads to the first practical algorithm for computing the eigenvalues of a general matrix, the QR algorithm using a Francis QR step. John Francis developed this in the early 60s, and I believe it was developed independently around the same time by someone in Russia, but unfortunately they never seem to get the credit because you never know what's happening over there. And the thing is, and he did this while working in industry, and he went on to do something else. He might have become a priest, but I'm not positive. I might have a detail wrong. But he just left mathematics altogether. Now, in 2000, they named the top 10 algorithms from scientific computing in the 20th century. One of them was, for instance, the fast Fourier transform. One was just the whole notion of matrix factorization, which has been a major theme in this class. And this was one of the algorithms too, the QR algorithm. So it's named one of the top 10. And so he's out of the math game. He has no idea that he's really freaking famous in the American algebra world. So in 2007, my advisor, Gene Gollum, tracked him down and let him know that he's famous. So at least he found out before he died. Well, I think he's still alive, actually. I'm not sure about that. But unfortunately, my advisor isn't. But yeah, so it's funny how these things work. So if you innovate mathematically, you want to keep tabs on it because someone might have discovered it and made you famous about your knowledge. Okay, but I remember when I was studying this for my qualifying exams as a first-year PhD student, that just seeing what the inventors of this method, because I mean, Francis building on what others had done before him, had to do to come up with this practical procedure and all the pitfalls and how we got around them, and fully understanding the transformations involved, like arriving at the implicit Q theorem and understanding the uniqueness of the Hessenberg reduction. And I had to wonder, because I don't really know, how did one think of that? Was it playing around with matrices to see, this is what happens? And they begin to pick up on it and like, maybe there's something that can be proved here? I don't know, because back then, I mean, the computers were not so hot in those days, in the 60s. MATLAB would not be invented for another 20-something years. And even if there was MATLAB, and programming was such a pain back then. I don't know if I told you all about what I heard it was like at my undergrad alma mater, Purdue. Before we had a computer of their own at Purdue, they had a guy who was a driver/operator. So he would go around to everybody, or faculty at the end of the day, and gather for programs that were on punch cards, and drive to the University of Chicago, and run the programs on their computer, gather up all the output, and then drive back, and then in the morning, he would deliver the output to all the users. And so think about any programming you've ever done. and how many times you've screwed up. Can you imagine how careful they were back in those days? Something that's been totally lost. So, I mean, these specific people understood that it's actually more efficient to multiply by 1/2 and to divide by 2, because the division is the circuitry for division is more complex than for multiplication, and nobody cares about that now. So, so that makes it all more remarkable. All these things that happened in the '60s with numerical linear algebra to develop these algorithms and also prove things about them with so little resources. So, and it definitely make us feel like schlubs, but yeah. And again, it's easier for him to, and it's a lot harder for us to build off of our research accomplishments because they're starting at a much later point. But and who knows how many of us could have invented the QR algorithm if it hadn't been already. Okay, so that concludes the story time. Okay, so let's see. So the overall procedure is so you just keep carrying out this implicit double shift, this Francis QR step, on an unreduced block. So what would happen is you have your full matrix at first that you're applying this Francis QR step to, and you carry this procedure out a few times, so maybe 4 or 5 times, enough to make that last subdiagonal entry 0. Then what you would do is then the eigenvalue problem decouples, so then you have that upper left n minus 1 by n minus 1 block. That's still an unreduced Hessenberg matrix, then you go to work on that. So you keep picking up off these eigenvalues one at a time. And sometimes I've done this in MATLAB, where I pick out the proper shifts, at least, and carry that out just to see what happens step by step. I can see, oh yeah, that really does cause convergence to a quasi-upper triangular matrix faster than not doing any shift. And then you can, once you get to a point where either the entire subdiagonal is 0, which is what is happening if you get real eigenvalues, or you have these either 1 by 1 or 2 by 2 blocks, because once you have it reduced to a 2 by 2 block, that's easy to get the eigenvalues of. So you just keep working on these smaller matrices until you've made as much of a subdiagonal 0 as possible. And then you have all the eigenvalues. Now, what I've not talked about here is so everything I've described is about getting not eigenvalues and eigenvectors, but the Schur decomposition. So the result of the QR algorithm, which is distinct from the QR factorization, is I mentioned this a couple classes ago, the real Schur form. A is equal to Q, T, Q transpose, where T is quasi-upper triangular with, as I mentioned, the log of 1 by 1 or 2 by 2 blocks, diagonal blocks, for either real or complex eigenvalues, respectively. So, what if we want a decomposition like this? PDP inverse. In other words, if A is diagonalizable, where P would give us the eigenvectors. So how are you going to do that? So really what you have to do is work on t once you've gotten it. So once you've reduced a to this somewhat upper triangular form t, so to get eigenvectors, assuming you can even get all of them, because A might not have a full set of eigenvectors, you have to find a matrix Y so that Y inverse Ty is equal to a diagonal matrix D. So then what happens in that case is that A, which we already know is Q, T, Q transpose, but now from this I can fill in something for T, Q, Y, D, Y inverse Q transpose. Okay. So then this matrix, Q times Y, would contain the eigenvectors as columns. Now, if we take a look at this problem here, if I multiply both sides by left by y, I get ty minus yd is equal to 0. Now, I know what d is. D has only the eigenvalues in a diagonal. And I have the eigenvalues because they're on the diagonal of t. But this is actually a hard problem to solve because the unknown is y. It's a matrix. How am I going to get a matrix y that satisfies this equation? So there is an algorithm, like it's not in my book, but in Calvin Van Loan for solving this problem. But the thing is, now we no longer have orthogonal similarity transformations. The matrix y might be ill-conditioned. So for an unsymmetric matrix, we actually have a whole lot more work to do to get the eigenvectors. Unlike the symmetric matrix I'll talk about on Monday, the symmetric case, the surety composition gives the eigenvalues and the eigenvectors because t is diagonal. Now, an alternative for you. Suppose you don't want all the eigenvectors. If you only need a few eigenvectors, use a different approach, which is called inverse iteration. Now, inverse iteration is actually a method we saw earlier, the power method. Applied to A minus lambda I inverse. So you solve A minus lambda identity. Zk is equal to Qk, and then, or Qk minus 1. Qk is equal to Zk normalized. So that's the algorithm carried out in an iterative fashion. So you choose a random vector to start with, a unit vector like Q0. Solve this system, and then normalize. So now can anyone tell me, when I covered the power method some time back, what does the power method actually give you? What's the result of applying a power method to a given matrix? doesn't give me all the eigenvalues or eigenvectors. What does it give me? You don't remember?
It gives you random one.
Yeah, the largest eigenvalue and corresponding eigenvector. Well, power method applied to this will give me the largest eigenvalue of this. But because we have the inverse, that's 1 over the smallest eigenvalue of A minus lambda identity. And what is that? That's the eigenvalue closest to lambda. But the thing is, my lambda here is one of the eigenvalues I have already. Or it's close enough except for round-off error. So this matrix is technically supposed to be a singular matrix, but because of round-off error, it's actually going to be just badly conditioned. It's going to be close to singular. So I can still solve this system. And because this is so close to an eigenvalue, I probably only need to carry this out once, and bam, it converges. But solving the system is still expensive. A rule of thumb that I've seen is that if you only need like less than 25% of the eigenvectors, you might as well just use inverse iteration to get those select ones. If you really do need all of them, or nearly all of them, like half or something, then going through this kind of procedure is probably more efficient. Okay, so at least we have an approach for getting eigenvectors, but it's for the unsymmetric case, it's not easy, and this totally doesn't even get into the fact that A might not have n linearly dependent eigenvectors. N might not be diagonalizable, and you don't know. So you might try to solve this problem and not be able to. So, yeah. And this is why the symmetric case is so much easier. And that's something I will talk about. Oh, wow, I'm slipping. I've gone 3 minutes over. Sorry. Okay, so I'll talk about that on Monday. And I'll pick out some nasty problems for you.